Okay, I think we're live. Okay, welcome to another live stream of Houdini with bubblepins. So today we're gonna continue off the procedural modeling. Sorry, one second. I have an echo on my mic. Here we go. Sorry, there was an echo on my mic. The signal was being broadcasted back, relayed back to my other monitor, and I accidentally turned off the mic in while I was trying to get rid of the echo. My apologies. Okay, as I was saying, to thin air. We're gonna continue off with the procedural modeling series, and last week we explored different ways where we can use different examples. How we can use the Vellum solver in Houdini to create different kinds of scenes, how to create different kind of geometry using the Vellum solver, and that was a very brief overview last week. It wasn't really the intention last week to be an overview. It was actually intended to be like a deep review, but I went on too long with the because I had way too many examples to show you. And today we're gonna go into a little more in-depth, sort of like an explanatory, more explaining, deep overview of like some of the parameters of the Vellum solver in order to create, and we're going to focus on the paper effect, using Vellum solver to create a paper effect, a paper scene effect. And if you recall from last week, I had 3 paper examples, I believe. Sorry about that. I had some basic concepts which we're going to go build up towards it, the bigger example application of using Vellum to create a paper effect. So we're going to start with basic concepts, but I'm going to show you what I have in stored. This is the trash can scene that I've shown a few times actually, and we're going to go in a little more in depth with this, using Vellum solver to create scrap paper. Just going to quickly play this. Oh, the trash can is here. So I'm going to talk about how to wrinkle them, different techniques, and once you actually throw in the textures onto these paper, it really makes a difference, and it really sells the look that this is scrap paper being thrown into like a can of trash. So that's one of them. The next one is a new one, actually. I didn't show last week. I just added it this week in one of my ideas that just light bulbed in my head over the weekend, is tearing. So this is sort of like a coupon tearing. That's what I was aiming for, like a coupon tearing. Actually, there's a better render I've done. So this is playing real time with Blender Cycle, so it's a little blurry. I do have one that's rendered out. I've posted it on my Instagram, so maybe I'll just play that, just to show you what it's in store for today. So I'm not gonna go too in depth, not like last week. Just briefly show you. This is the paper tearing scene. So this example is new. This is something I came up with in a few days ago. So this is sort of what I was aiming for, was like this coupon. So each of these squares is like a perforated square coupon where you tear off of like a larger piece of multiple coupons stuck up on a perforated paper. So I really like this. This is actually quite simple to do with Vellum. So these examples are awesome. That's why I like they're very effective with Vellum, and they're not overly complicated, or at least I don't think so. I'll let you be the judge of that at the end. And the last one that I have in store for today will be, just gonna grab it. It's loading, give it a second. Okay. Camera. Flyers. Okay. Would be this flyer scene where we turn all these posters plastered all over this small city block, and there's wind force applied to the Vellum solver, and it blows them around the place. So these are the 3 scenes that I'm going to demonstrate how you can apply the basic concepts, which I'll go over today. Sorry, just let me get a drink of water. So we're going to go over like some basic concepts that I want to get out into your head first, and then we're going to apply some of those concepts and create that scrap paper, the coupon tearing, and this poster flying all over the city look. Muddy Creek Critters. Hi from Ohio. Hello. Nobi Danino user here, hoping to get some tips. Awesome. I hope you'll find it useful. Hello, Joanne. Birdie Academy. Nice to see you again. And Andrea. I hope I pronounced that correct. And Andri. Hello, Bubbles. Here's Andri from Brazil. I love your tutorials. I learned a lot from you. Awesome. Thank you so much. Thank you for watching. And I'm sorry if I mispronounced your name. I'm not very good with names. I do try, though. Okay, let's start off with the basic concepts. Just get rid of this. And I'm just going to close this because I don't have much RAM. Okay. Just going to get my assistant program running. So I have this little assistant program that keeps, that helps me create these overlays. So these arrow overlays or these rectangles that will help me explain things more clearly. And I've added a nice feature over the weekend, is that it'll automatically disappear after 3 minutes, hopefully, if the screen has changed. So I made that a little fancy detection. I hope it works though. I haven't really tested it very thoroughly, so it's still like beta. Birdie Academy, I love when you make example in big scales. Awesome. I like how the Vellum solver makes it really turn out really nice too. Let me get my notes. Oh, did I accidentally close my notes? I did. I'm sorry. Just give me 1 second. I have to reopen my notes. I accidentally closed it. Okay. I have been meaning to upgrade my main hard drive to a faster hard drive because right now it's running on a really slow SSD. I wanted to buy one of those fancy NVMe drives and then transfer all my stuff from the main drive, which is like the boot manager, along with like all the OS partition onto it, but I haven't figured out how to do that yet because I just want to clone it. I don't want to reinstall all the software and all the applications. All right, here we are. Okay, the first example we're going to go over is a basic concept one. So this parameters here that you see here, it's just a nice fancy way for me to have all the parameters in one node in one place so I can easily find it. I don't have much here. It's just that I have a very limited hard drive space that I go through hard drives like butter. And it's I have to put things on different partitions. So this is a way, this is an environment variable I set up that points to a different partition, a faster hard drive set up on my computer, which allows it to load the all cached files a lot faster. So this is just a fancy way, and this is, you can see it's part 2. All the cache is made from part 2 because these examples were made last week, except for the coupon tearing one. That one is new. So that's all this is right here. So you can ignore that if you don't like it. Okay, let's begin with the first example, the first basic concept one. It's a very simple one. So it's all I have here. Now you might recognize one of these. I also want to mention from Procedural Modeling Part 1 video, I had mentioned that relative size was very important in the procedural modeling workflow. So that means that you have one object. Here is our grid. Let me turn this darker so it's easier to see, and get rid of the grid. Okay. So we have one object here, which is the grid, and we have another object here, which is the rubber toy. And they're both relative to each other. The size is relative. That means if I increase the size of the rubber toy, so I'm going to increase the size here. Actually, this is a good time to use that fancy if I increase the size of this rubber toy, you can see that it's this rubber toy is growing bigger, bigger, and so is the grid over here. So that's also growing with it. And the importance of having relative linking the sizes between the two in procedural modeling is that when you go through, this is a very simple example, but if say you have a very more complex scene and you have tons of nodes, like, I don't know, 50 nodes in your node network, and once you're done and you decide to change that one thing, you just decided to change the size of the rubber toy. You want everything to flow automatically. You want like the grid to automatically grow with your rubber toy size. You don't want to go in and fiddle around, change one parameter, but you also have to change 10 other parameters. So having it linking has that procedural modeling workflow. It's a good practice. It's not a must-have. So probably it's a good idea to have as a final product if you're creating a digital asset or anything like that, a reusable asset. When you're concepting and just building a prototype, I think being messy, it's okay. Okay, enough of that. Let's go over this simple example. A very simple, let me get rid of that template. I'll ignore this because this was just to make it bigger. So it's not too much. It's just a cloth, the grid being turned into a cloth. I drop it onto the rubber toy. The cloth is designed, Vellum cloth is designed to be flexible. It's soft and it takes the shape of whatever it easily takes the shape of another object when you apply a force to it. And the force that we're applying here is gravity. So gravity is pushing the cloth onto the rubber toy, and we're getting this. Shapes. So that's super simple. We have a Vellum post process, which increases the topology of the cloth. It subdivides it, and it looks way better now, right? This really looks like a cloth rather than this. This has more topology, so keep that in mind. There's more points. There's a higher poly count. So this would have 1,369 points, as opposed to this one. This has 100 points. So it's quite a big difference. Let's take a look at some of these comments. Christina, I love the way you explain things. Thank you for doing this. Oh, thank you for watching. Okay, so this is a very simple example. That's concept number 1. Now let's move on to concept number 2. Just give it a second. I'm just going to copy it. Okay. Now this is concept number 2. Now you can ignore this black node network box, small box over here. It's only there for the labels, and I'll show you what I mean. Let me take this out. Okay. It's the words down here where I have, so it's these labels. Oops. Okay, it's those labels that is this part over here that's creating it, and it's only there for visual purposes. So it won't be used. It's not practically used. It's only so it helps and aids in my explanations. So we have the very similar example here. You can see that I have the relative size, you have the grid, you have your rubber toy, and we're not doing much here. Let me put the render flag here on the Vellum solver. I'm just going to run it. Oh, I should show you the labels. So, okay, let's put it down here with the labels. Let's ignore this post-process. I apologize for the labels moving. I didn't want to go too fancy. It's just, it's matching the size of where the position of the grid is, and I just moved it down. Nothing fancy. So it is, the labels are going back and forth just because the cloth is moving as well. Now, what I wanted to show you here in this example is the high stiffness and low stiffness value of the cloth. So over here on the left side, I have a high stiffness value. And I can show you what the stiffness value is. It is this one here. Now I think it got cut off too. I'm not sure if you can see this. It is 1, 2... It is 1 to the 10th, the exponential 10th. So this is in the, let's see, 6, 9, 10 billion, 1,000 billion, which would be a trillion. This should be a trillion, a value of a trillion stiffness on the left side. And on the right side, let's take a look. It would be this one. Low stiffness. Okay, let me stop this for a second. The low stiffness. I had to stop the playback because the panel over here, the parameters panel, wasn't updating. If you're playing it back like this, and then you choose a node here, it won't update. Anyways, this one on the right side over here has a very low stiffness value. It literally has a stiffness value of 1. And it's very, you can see that it's very fluid. So this one is very, very fluid. It's more cloth-like. As opposed to the other one. This one is a higher stiffness. You can see that it's harsh. It's very, very harsh. These folds are harsh. They're very hard folds. It's not very fluid. It's very rigid, which is perfect for paper look. If you're doing like crumpling up a paper, this is what I'm imagining. When you're doing using your A4 printer paper, and you're like someone's writing a story or someone's scripting and they're struggling, they're frustrated, they write a few words and they crumple it up and then they throw it on the ground. So this is sort of like that fold, that harsh fold lines that I really like. to really sell that trash can paper look. Now, so this is the difference. To help sell the paper look, a high stiffness value is nice to have. Now I want to show you what happens if I increase the resolution of the original grid. So right now the original grid is 8. It is 8 by 8. So we have a total of 64 points, which is a fairly low poly count on the grid. Now what I'm going to do is I'm going to increase this 64 points, and I'm going to increase it. I'm going to double it, 16. So now we have 256 points for the grid. Okay. Now let's play it. Now, the one on the right, let me zoom in a bit. The one on the right over here with the low stiffness value is more, it's turning more fluid. It's becoming more cloth-like. The one on the left is still, it's actually getting more fluid too, as opposed to, now let's do this one more time. I'm going to turn it back to 8. I'm going to play it again. This is very rigidy, right? Now let's do it 16. It's still very rigidy over on these edges, but if you look carefully, it is getting more curve. It's getting more that shape, that curve shape, cloth-like shape. It's really hard to tell because of these sharp rigid bends, like it's like a stair step. But it is indeed getting more flowy. So what we're going to do is turn it up again. So instead of 16 by 16, I'm going to go 32. So 32 by 32. And we have 1,024 points. Let's play it again. Now this really shows that the high stiffness value on the left is becoming more cloth-like, even though we have a very high stiffness value. So that's one of the things that you need to know about selling that paper look. Low poly count, high stiffness value, and one more thing I'm going to add to that list. Now, I'm going to come down here and I'm going to enable this Vellum post-process node now. Right now, it has one subdivision level. It has one subdivision level to smooth it out. Now that instantly creates a more cloth-like for the one on the left. It instantly turns it into more clothy. Because, well, for one thing, we have subdivision turned on, like we're subdividing it a bit more. So it's getting more smoother. It's smoothing it out. And we have a even higher poly count. So let's take a look at the poly count. Over here. 7,938 points. Oh, but this is both of them combined, I guess. That's not very fair. Okay, let me do this. Let me go over here. Because this Vellum post-process is linked to both grids. So to be fair, I'm just going to manually select this out. Okay, this one. Let's blast it. Oh, what happened? Now this will blast it. And I only want that one. Just this grid. And I want to see how many points we have. This has 3,669 points. So it's almost 4,000. 4,000 points. And the original grid is here. This is just one grid. Was knocking down 1,024 points. So it's almost double just because we're subdividing it. So every single time you subdivide it, it increases the poly count and makes the geometry much more smoother, which results in a more cloth-like look. So 3 things to take away. High stiffness value. To really sell the paper look, high stiffness value, low poly count, and try to avoid using the Vellum post-process node. Now let me turn this back to 8. So we have a low poly count. So the paper look is on the left. Now there's one more thing I wanted to mention here. For these Vellum constraints, I've put down a very high damping ratio. Now the damping ratio, the default damping ratio that it comes with, so let's right click this and go return to default. So it's 0.001. Let's do that for both of them, for both examples, the left example and the right example. The return to default. Oh, I think this one's already default. Okay, let's play it now. Now what I want you to see is the bouncing effect this one has on the right. The one on the left doesn't really have much because it's really high stiffness. The one on the right is bouncing excessively more. Look at that. Bounce, 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 bounce. Okay, let me show you again with a low, with a higher damping value. 0.1 was what I had. So let's play it again. Now this doesn't have as much bouncing. This one doesn't have as much bouncing. When you increase the value of the damping ratio. Now let's do it one more time so you can really see that. So bounce, 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 bounce. Because I've lowered the damping ratio to 0.001, which is default value for the damping ratio. So if you ever have this kind of issue, this usually happens when you have low stiffness values, though. You can see that on the one on the left side, that problem doesn't exist, even with a low damping ratio. Because the damping ratio for the high stiffness one on the left, I haven't changed at all. So it's always been 0.001. Just something that to be aware of. If you have this shaking effect that you really want to get rid of, just increase the damping ratio to something like 0.1. Don't go too far. Like try to stay below 1, I think. Otherwise it might the Vellum solver might not like it once you go above 1. But you can always try and see. That trial and error is the best way. High poly count, Vellum design. Okay. Now the last concept I have, just grab that example over. Again, we have the same sort of setup, a very, very similar setup. We have that same, like that again with the grid, and I'm dropping it on top of the rubber toy. Very similar setup. And I have this linking the match size, so I'm linking the size. We have a relatively high stiffness value set to this grid. It is 1 trillion again. For the stiffness value, it's 1 trillion. Now let's try this. The only thing that's different between this example here, I'm trying to hide the stuff on the bottom before I give it away, is this node over here. This is the these 3 nodes. But these 2 nodes over here are mainly just for creating groups for the polygon, for the edges. I'm trying to grab the edges. So this really doesn't make any real effect to the geometry. The real magic happens over here on this attribute wrangle. I'm going to make this a little bigger. In order to make the text bigger on the attribute wrangle, hover your mouse over the text box area, click it so you have the cursor here, and go Control plus. So, in case anyone was wondering. Okay. You know what? I'm going to break this out. It's probably easier. Okay. What this is doing here is, now let's take a look at what is happening before the attribute wrangle. So over here, this is just a simple grid. The points are evenly, it's in a grid-like pattern, the points are all. And once I go into this attribute wrangle, the points are being randomized. It's still flat. I'm just trying to show you that it's still flat. I'm only shifting these points. Oh, that's not enough. The points are not big enough. Okay, hopefully that's a little bigger. So the points are being shifted left and right, up and down, but not up and down. I mean, like, it's being shifted on the plane. It's being shifted around the plane. It's still flat. It's always flat. So I'm randomizing the X and the Z because Y is the up and down. So I'm not touching the Y. The Y is always wherever it's right on the ground. I have a seed value. I have a range. The range allows me to shift the points a certain amount. So it's to prevent this. So I'm going to take this range over here and I'm going to really turn it up, and you'll see what starts to happen. The points get really, really out of place. It's exceeding. It's actually like ruining the geometry. So that's why I have this here. It's to adjust the range, so I can manually control the range without going too crazy. Okay. Now the seed value is to create to get a different random. If I didn't like the look of this and I wanted to change the look of this, I can just turn the seed value to something else, and I'll just get something different every single time. What I'm doing is I'm just adding a random number to the existing X and Z values, and that will shift the position of it from left to right. Just because you're adding a bit more, and I could be adding a negative number. So the range is, I'm saying the range is 1.2, but I'm actually taking negative range and positive range. So it is negative 1.2 to 1.2. So that's the range amount I'm adding to the existing X and Z. So if we go over here to the points. Let me pull this up, actually. Yeah, if I go over here, these points are... Oh, another thing to mention is that I'm not moving the points on the border. That's why I needed these two nodes to group this border. And once I enter this attribute wrangle, you can see up here that this attribute wrangle is taking everything but the border. So there's the exclamation mark is sort of like the inverse. Do something to everything but the ones with the border group. So I'm taking all the points that are inside and not on the border of this grid, and I'm shifting it around the place using a fit and a random function. The fit will make sure that the random number returned, here I'm getting a random number, and make sure that random number returned is within the range that I set over here. Which is the range in this guy over here. So hopefully that makes sense. And all that number, so this number is always in between negative range, so negative 1.2 to positive 1.2. Any number in that randomly chosen will be added to the existing X and Z position. So the at P, that gives you the position values of each point. I'm just adding, it could be a negative, remember? So we could shift left and we can shift right. So I'm adding a random Z and a random X and random Z values to it. So hopefully that makes sense. And all I'm getting here is that I'm getting a random topology for this grid. Now, why would we want that? Well, let's just play it. Let's just play it and see what happens. So the purpose of doing this was to randomize and to control, sort of give more control to where the folds. Because if you notice carefully, this paper look I'm trying to sell, it's folding right on the lines, the topology lines of this grid. So if I make, the only problem with folding on a perfectly straight grid like this is that it will only fold on the evenly distributed lines. If we want something more interesting, we're going to have to randomize the position of these lines. I mean, I still want the paper to be a square shape. So we're going to randomize all the points inside. And this will control where the paper folds and give a more random look. Like, this is a very small grid. If you want something like a little bigger with more folds, more wrinkly, more crumple-like. So this gives a way to control where the folding happens by controlling the topology. Now, something to mention that, because this is a very rough look. So let me take out the points. This is a very rough look with the paper. You might want something more with a higher quality. And I mentioned that we want to avoid using the Vellum post-process. Now let's see what happens when we do use it. It gets very smooth. Like, this loses the paper look, right? Let me template the rubber toy. It loses the paper look. It really does look like a cloth now. A really stiff cloth though. Okay. So one way to still get the high quality but keep the rigidness of the paper is to maybe use the subdivide. I've noticed that the subdivide with this bilinear open subdivision bilinear selected, it will not smoothen the edges out. It won't smooth it out. So you still have that rigidness. Now let me turn this into flat shaded so you can really see it. So you still have that harsh fold lines while still getting that higher quality look, or getting that extra topology that you really need. That's one way. I was also playing around with this and found that if you add a poly bevel to it, you can create different effects. So this could be like, let me turn this back to flat wire shaded. This can be like different folds, like embossing. So you can see here on the, let me go back. Here on these fold lines, here's the poly bevel. We have more lines, and it's sort of rounding out these folds to create a different look. If this is a look that you're looking for, who knows? This might be a really thick piece of paper that you're trying to fold, and it might not fold all the way, and you might like the look of having a harsher fold and not as sharp, like you have a thicker fold. You can also control how much the bevel to do by controlling the distance of the bevel. So this, for a thinner look, for thinner, but still that little, this edge, round edge here, as opposed to a sharp, as opposed to this sharp fold over here. So that's something you can also do. to compensate for not having the vellum post process. Okay, those are the three basic concepts I wanted to go over, and let's try and apply this to a more applicable, practical example. Now let's start off with the trash can. Give me 1 second, I'm just gonna paste it in. So here's my Vellum trash can. I started off with one grid, but I do a copy and transform, so I needed more than one piece of paper. Now we have several papers, just because it's a trash can full of scrap paper. The UV wrapping, that's super simple, because there's a UV square for each grid. So let me just quickly show you the UVs. So that's like a UV for each grid. Now you can set a UDIM for each grid as well, but I thought that was a little overkill, so this was fine with me. Okay, now I'm just going to show you. This time, let me take out the UVs actually, because I want you to see the lines. I want you to see the fold lines. This time, I use a Vellum drape to actually create the wrinkling first before it drops into the trash can. So a Vellum cloth constraint is applied the same way as we do before. This is a stiffness value of 1. I could make this a trillion, but it didn't really make much. It didn't. Let's play it with 1 first with the Vellum drape, and then we'll play it with a higher stiffness value. Okay, let me get rid of my cache and let's reset the simulation. So the Vellum drape node is really for sewing clothing together, for like jackets, for making jackets in jackets, clothing, pants, shirts, scarves, collars. It's mainly designed for clothing. I've thought it was neat to be used for scrap paper in this case. Now you can see here these white lines on these grids. These are sewing lines. So I really should show you what it really is used for. Let me grab. I'm going to play this example, and then I'm going to find my other example of the clothing. Sorry. Because for some of you that may be new to the Vellum drape, this may not make much sense to you. And I have a quick example right here. I just have to open it up. Okay. And I just want to show you what the Vellum drape was designed to be used for. It's not really for making scrap paper, but I thought it was neat that it can be used for scrap paper. So I have these sewing lines here, and it's pulling the paper toward the points that I have selected. And that's the points over here. Here. In this dialog box. For this guy over here. So these are weld seams. Or it's called weld seams. Okay, here it is. Cloth, vellum. Drape. Alright, there we go. It's loading 1 second. Why load? Why is this loading? preview window. Okay, awesome. There we go. Oh, stop loading. It's cooking on the other side. Okay, there we go. Oh, it's cooking everything. No wonder what it was doing. Okay, I might as well just drag this over. That was a silly thing to do. Okay. I know. The size is wrong because my other monitor is a different resolution. But let's see if we can make this work. I just wanted to show you quickly what the Vellum drape is actually doing. So this is the Vellum drape node was designed for clothing. And here I'm making a really simple jacket, which was one of the examples from the previous video. And what it does, it pulls, you can see those same white lines here. And it's going to pull this, wherever there's a white line, it will pull it together in order to create that jacket. So that's what it really does. So it will pull wherever there's a white line. It's sort of like, this is the attraction force that will be holding this piece of clothing over here to the other side. So I used this concept to pull the paper together. So that's where these sewing lines come in over here. But this is paper. I'm trying to create paper. And I'm just pulling it from this point to that point. Let's see if I can show you where this point is. This one's on the bottom. Let's go down. Okay, we can actually... Okay, let's create another one. Let's create another sewing line. Add one. And of course it puts it on one. Okay. Now I'm just going to randomly pick a point here. It doesn't matter what point. So this point over here. Enter. So you can see that a new point number has been added over here. Now it needs to pull against another one. So every sewing line needs a pair. So I'm going to choose another point. Let's pull this corner over here. Enter. So you can see I've created a line down here. I don't know if you can see that. There's a line right here. So there's a line pulling together that will pull it together when I run the simulation. It will scrunch it up here. So let me slowly play the Vellum. So that's where all the scrunching up comes in. And that's where I really get that wrinkle look for the scrap paper. And I just pick a frame that I like. Like, okay, this is scrunched up enough. We're on frame 29. Go to the Vellum drape. Go scroll all the way up. Freeze at frame. So here it says freeze at frame. So here we have frame 29 is down there. So I'm going to put 29 up here, and I'm going to enable this freeze at frame 29. So whenever I change this timeline down here, it's not going to do anything. It's not going to cook. It'll stay on that frame. And even better, you can even cache this. So there's a cache enabled here. You can choose, click this button, save to disk. It'll save it in wherever you want. And then you can check this load from disk. So it'll always be available for you unless you move your cache. This will make it a lot faster so that because every single time you start Houdini, it will re-simulate up to frame 29, even if you reset the play line to frame 0, because it's frozen on 29. This is sort of like a simulation within itself. It will always have to cook until frame 29. So this caching it will speed things up, especially on launch, when you're launching the scene multiple times. Hyson, hey, good day. I have a question. How to deal with intersecting wrinkles and giving you reversed face normal. Oh, To reverse the face normal is super easy. Just reverse. Throw down a reverse node. So let's see. If we have a grid, it's like this. And say it's flipped. No, it's not flipping it correctly. So it's flipped. So this has reversed the normals on the other side. If you drop down a reverse, it will flip it. However, if sometimes you have, for some strange reason, you ended up with flipped normals for the ones in the middle. Okay, let's turn this back to 0. Primitive if... Oh, you know what? I'm just gonna choose a face. Let's go 5. And I'm just gonna reverse the normal. I don't know if I can though. Let's see. No, I guess you can't. But if you do get like a normal in the middle, like a primitive in the middle that has a reversed normal and it looks weird, you can always recalculate the normals. So throw down a normal node and this should fix it. And if this doesn't fix it, it means that you already have normals on your existing grid. So if you go over to your spreadsheet, sometimes you can have normals on the points, on the vertices, or on the primitives. And if that happens, adding this normal here will just may or may not fix it. What you should do is clean it up first. You can drop down a clean node, or you can drop down a delete node, attribute delete, and just clean it up. Remove, check here, remove attributes, and remove the normals instead of removing everything. So the asterisk will remove everything. Sorry, that overlay was very annoying. I forgot to delete it. Yeah, you remove the normals before you add a normal attribute here. And you have to choose something like, I don't know, primitives or whatever you need. I would usually use primitives. It makes it look better on the display port. So hopefully that answers your question. And I think that this triggered the Vellum drape to calculate again. Okay, there we go. So there's that wrinkling effect. Now we have to dump all these wrinkly scrap paper into the bin. And for that to work, I use the Vellum solver. Okay. So here it drops it all in. Now you can see it's quite flimsy, just because I have a very low stiffness value. Now this is a good time to increase the stiffness value. Oh, it's already a trillion. Oh, or I think it's not a trillion. Let's see. I think it's a billion right now. 10 billion. Well, let's increase it 100 more. But once you increase the stiffness here, you have to remember this Vellum drape node here has been cached out. Like it's frozen on frame 29. You have to reset this. So all changes you make above this here, like everything above the Vellum drape, has to be recooked again. If you have this freeze at frame, or if you have load from disk cache, if either these two are enabled, everything above, ooh, sorry, that's a really large arrow. Everything above the Vellum drape node has to be recached. So that's something to be aware of. Since we have increased the stiffness value, I'm going to have to recook this Vellum drape node and then reset the simulation. So it's going to cook. Okay. Freeze at frame. Let's just play again just to see what it looks like. Freeze it at that frame. Now let's, I forgot to, okay, there we go. Throws it in with a higher stiffness value. It's still a lot bouncier than I would have liked. So that's how to get the scrap paper look. Now, the scrap paper look looks a lot better with textures. So this is stuff without textures. And again, here I have ignored the UVs. So there's no UVs to this right now because I turned off this node. Let's turn it back on. And again, once I turn this back on, even if I recook this, it's still not going to show the UVs, or it's not going to show my textures till least. Look. Sorry, I changed the geometry node name. Okay. But you're not gonna see the textures come out just because we have to recook the vellum drape again. So let's do that one more time. Come up here. Oh, I don't even have that texture in there. Sorry. This is what happens when you separate the folders into different every project into a different folder. Paper textures. Okay. Paper UV mapping. Scrap paper. Okay, here it is. Texture scrap paper. Okay. It's just in the wrong folder. Scrap paper, UV mapping, this one. There you go. Now let me ignore this. I just wanted to show you that the importance of recaching. Okay, there it is. Now when I enable this, it's not going to show until I recache this. Reset simulation. Okay, there it is. And it comes up. And you have to have this button enabled too. If you're wondering, okay, I recached it and still I don't see my UVs, or I don't see the material that I've added to it, it's because you don't have this button enabled. Just make that arrow a little bigger. You don't have this button enabled, which enables the textures that you've applied using this material node. So if I turn this off, it's off. You won't see it. You'll see the UVs, but you won't see the text, the material you've applied to it. Okay. So having the textures on really sells the scrap paper look, is what I wanted to say. Now this would have been much more, even more convincing if you notice here, if I had added more noise to the topology. So in my previous example over here, we're controlling where the wrinkles appear using noise by messing around with the topology like this. If I applied this to the scrap paper look over here, to every single piece of paper, I think it would be even more convincing. So that's something I could have done to enhance the scene even more. Let me just check my topic list. Low polygon. So yes, another thing I want to mention is that this sort of keeps that low polygon that we've learned to sell the paper look, because every grid is pretty low. It's 10 by 10. It could go even lower. but I wanted it to all fit in the bin to look like it was really full. So I did add a bit more topology, so 10 by 10 rather than the 8 by 8 that we had before. Low poly count. Use topology to control the folding of where the paper is, using the Vellum drape node this time instead of, so the only difference is that here, this scrap paper example, we're using a Vellum drape node instead of dropping it on top of the rubber toy, because over here in the basic concept number 3, I'm using gravity to control the folding, because you need some sort of force to push the paper toward it inwards towards itself, to push the paper, to squeeze the paper in order to wrinkle it. You need some sort of force. Here we're using gravity, and we're using the rubber toy as a force to push it. For the scrap paper, I use a Vellum drape node instead. In order to squish it together. So that's the force that I'm using. And then the Vellum solver takes over and uses gravity to throw it into the bin. The gravity is pulling it in towards the bin, but it's already wrinkled. So half the work is already done. So that's an example of the scrap paper and the coupon tearing. So this was really fun to create over the weekend. Let me just grab it on the other side. So let me just play this to double check. Okay, you can ignore that, all this purple. It's because I have the visualization turned on to look at the stress. Let me turn that off. And I'm pulling, I'm tearing off a coupon. Now this looks a lot simpler than what I have displayed. This looks like a lot of stuff, right? Most of this is grouping the edges of this coupon. So let's take a look. Let's take a look at this. Hassan, thanks, Miss TBH. The trick of the clean it first, it works with some of the faces, but when it intersects, some faces got reversed, but way less than previous. Maybe I haven't dropped my question in proper way. What kind of geometry? Hassan, sorry if I butchered your name. What kind of geometry do you have? Are all the faces connected as a watertight geometry, or do you have something like a grid like geometry, one with a flat grid, sort of one plane? So what kind of geometry you have? Okay, so back to this. So once you drop that in the comment, and then I'll see what I can think of in order to fix your problem. Okay, let's go back to this coupon tearing. This grid is over here. So 1 square for each grid. So this is a really small grid. It's a 2x2 grid. I have facet on. So what facet does, it unwelds each face, so that now I can go like this, pull it out. See, it's not welded together. So it's completely separate. So that's what facet is doing. Now I take that and I apply UVs to it. And all I'm really applying is my logo on each grid. So each square here is occupying 1 UV square. So I have 4 UV squares. So nothing special about that. Then that's like all this part. And then this here is mainly to label the coupons, or I call it a paper number. So this is paper 1, 2, 3, 4. Here we go. See, I'm just labeling and remeshing it. So I need better topology. I need some topology. Over here you can see that there is no topology. Let me turn off the texture. Let's turn off the UVs too, because it's not it's distracting. I'll turn it back on a little later. Right here, my 4 square piece grid has no topology, absolutely no topology in the middle. So we need some sort of topology in the middle. It's because we want the paper to fold. It needs to be topology for the paper to fold onto. And here I apply a remesh, but a very light remesh. So you can see here. Now let's take a look at this one. There's very little topology. It's not a lot. Like, don't go crazy with the topology. Otherwise, because we want to keep it low poly count in order to sell the paper look. So what this basically is doing here is labeling each paper and putting it into its own group. So this is paper number 0, 1, 2, and 3. And this will help me determine where to weld the paper onto, where is it perforated and where is the tearing going to happen, because that this grouping will help with all that, because we need to know where are the welding points. And here, so here, this is another for loop here that again creates all that grouping. I need to know where the edges of the coupon are. And here are the edges where it's not near any other coupon. So this is the outline. Outline, outline. This will help with the welding. So this one, you can tell that this coupon 0 only has points on this side and not in the middle. That's because I'm going to be tearing this one and it's going to be like coming outwards. It's going to be flying out of here. It's going to be going out this way. As opposed to everything else, like all this stuff. Here. Here. Let me change the color, active color. Okay. This, here, and here, all these points along here will have to be intact. This is more like one piece of geometry. This whole part. So all this geometry over here, all this red, oops, all that stuff over here, all 3 of these squares is going to be one whole geometry, and it's going to be welded onto this smaller square over here. And it's going to be welded to this smaller green square over here. So these orange points down here will not be attached to anything. I'm sort of saying this is the parts, these are the points to pull on. So all this is done with like fancy grouping. Now the reason why this is so complicated, because there's so much of this, is because I wanted to make this a little more procedural. This parameters over here has coupon number to tear off. Up here. So I'm making this more procedural to label the one I want to tear off. So if I switch this to coupon 1 and then rerun this simulation, let's give it a try. Turn off the points. Turn off the overlay. Okay. And it tears off that one. And let's take, where's my parameters? Here it is. I'm gonna, sorry. I'm gonna do this again. And I switched it to coupon number 2, so it's tearing off something else. Tearing off that one. Now I do have the reason why this is messed up is because the pinning, the points to pin it down is on the top. So that part isn't as procedural as I would like. So it makes more sense to tear off the ones on the bottom, because points up here, these points up here have been pinned down. And I've told the Vellum solver, do not move these points at all, because I need some sort of anchor for the whole thing to work. So you can see all this, I believe all this here is all grouping, point grouping. Now let's just go over some of these. Actually, let me show you what the Vellum solver setup is, and then I'll explain each group as we configure it in the Vellum solver. I think that's easier to wrap your head around. I would like to go over how I did the animation though. So there's 2 ways of doing it. One, the procedural way of doing it, which is some fancy Vex code. Oops. I'm trying to pull this out. Okay, here. Some fancy Vex code, and all it's really doing, so let's put the render flag here, and all it's really doing is moving it away, moving one square away from it. Now, depending on which coupon you have, you know what? I'm just gonna break this out so I don't have to keep panning it over. Procedural animation, here it is. So here this is more fancy in that if I change the coupon, so I'm changing it from 0 to 1 down here. So I'm changing it down here. I should really change the color back. Okay, I'm going to change it to 1, and then let's run it again. So it moves this one now. So now it's going to move a different square. And then let's go to 2. It moves that one. And 3. So this is just something really fancy to move the square away from the center. I'm using the center as the pivot. So you can see here, it's grabbing the center position of the entire plane. And then the center position of the coupon, which is each square. There's one of these square points. So the center position is here. And then you have the center position of the entire square, which is like here. And I'm moving it away. Oops. Okay, let me lower this. And I'm moving the square away from the whole thing. That's where this part is doing. It is calculating the direction. Takes the coupon center minus the center, you get a direction, which is what this arrow is pointing over here. After you get that direction, we get the frame. And then how far to move it? Well, the larger the frame value, then the more to move it, the larger the scale. So larger frame value, the larger the scale to move, the length to move it, which is, I call it a scale. So we just multiply it because they're proportionally increasing in the same proportion. The larger the length, the larger the frame. And I add that value to the existing P because the direction tells the P where to go. And the scale tells it how much. Just multiply it and add it to the P. Hopefully that makes sense. It's you have to dig up your trigonometry from high school math, and look up multiplication and addition of vectors. Oops, ouch. Let's see. So this is the fancy Vex version, procedural way of animating it. There is a more simple way. Just animate it manually. It works just as good. So here's the animation, manual keyframe animation. Oh, let me take out the overlays. So you can see down here, I have keyframes. 1 keyframe, 2 keyframes. So there's 2 keyframes down here. I don't know if this arrow's large enough. Okay, so there's 2 keyframes down here. And when I take this out, strong points. Oh, I forgot to update this. This is called selected coupon. Sorry, I had forgot to update the name. Okay, I think that will work good. So this is moving it here. Now that's one thing to be aware of. Once you change the coupon, you also or the paper to tear off, you also have to update your keyframe as well, your manual keyframed animation. So you can see here that this doesn't make sense anymore just because I had a different coupon selected before all this. So let's update this. Doing the animation is super easy. Let's take this all out and do it again. So we want the selected coupon over here. We want a keyframe on the first frame, because this is the 0 position. Let's put a keyframe here. Alt left click on the translation, and you can see all this turns into green highlights. That means there's a keyframe on this parameter. Now let's take this, take the timeline here, and let's move it forward, I don't know, to 36. Come over here, press enter, and I'm going to manually move this away. And I'm going to put another keyframe here on the translate. Alt, left click. And you can see this turns green. Okay, let's play it back. Yeah, that's pretty cool. Now let's play it. I had a switch here, so I'm going to switch it to 0, which is choosing the manual keyframe one. And let's see how it works. Let's see how it looks. Not too bad. The manual keyframe is just as good as the procedural one. The procedural one is a little fancier. So if you ask me which one to do, which way would you use it? I would, if you're only doing this once for one scene and you're not creating a generator or you're not doing anything, or I don't know, if you're trying to practice your Vex, or you're trying to have good practice, or trying to get the hang of proceduralism, yeah, I would suggest to do it the fancy Vex way. Other than that, if you're just doing it once, it probably make your life easier just to keyframe it, because there really is no point doing it the fancy way. If you're only doing it once. Now let's take a look at some of these. You can ignore this node over here. I'm just delaying it just because I wanted the first few frames to stay in place so people can actually see what's happening. If I ignore this, you can see that it tears up right away. And when you render it out, it happens so fast that nobody knows what's going on. So I had this delay placed in. It's not necessary. Now let's take a look. The cloth over here, constraints. Now I'm pinning these points. The points that I'm pinning down. Let's put it down here. You can see this here. These purple points up here are the pinning points. And what it does, it's telling it, don't move, or don't move unless you have this selected. down here, you can see that I have match animation selected right here. When this is enabled, it tells this, okay, don't move, tells the Vellum solver, ignore these points, these point groups, which are the purple points you see in the viewport, including the ones down here. These purple points, don't move it unless this checkbox is enabled, match animation. So when this checkbox is enabled, move these points wherever the animation, follow the animation. And what animation are we talking about? That's the animation that we did up here with the keyframe. This animation. But the thing to note down that this pinning is only follow the animation for these purple points, none other than that. So even though that in our keyframe animation it's moving the entire square, I want the Vellum solver to take over the non-purple points, only these pinning points. Let me take this and create a group so you can visualize this more clearly. Points. So these points will stay put. The ones on the top here, these points are not moving. Just because we're not moving it in this animation at all. The only part where this animation takes place is these selected points, this tearing this square away from everything else. This is the only match to animation that really kicks in. Even though we have it listed, everything is listed over here, including the top points up here. This match animation is really only affecting this square over here, just because animation is happening to only this square. But it is also pinning the ones at the top too. So it's telling the ones at the top do not move. And it's telling these ones over here move according to the animation. Hopefully that makes sense. Now we have the welt, and how do I get these points? Now the selected coupon strong points here. This group, okay, let me use this one actually. That's this one. That's these points. I need to know which coupon to tear off. So we already know which one I select because I have this fancy, here it is. I have this fancy thing over here where I specify which coupon to tear off. I specify it, and sorry, that box just went away. Okay. Subajet. Sorry, I'm so Sabajet. I hope I got your name right. Thank you. Thank you for your comment. Let's see. Selected coupon. Here's my selected coupon. Now you can see I have a split here. It splits off, and I have this fancy thing in the split, in this fancy H script right here for this split node. Okay, this fancy H script, and all it's saying at paper number. Now let's do this the harsh way. Let me get rid of this. Let me get rid of this. Okay, let me get rid of that, and I'm gonna put a 0 here. Enter. It will have the same effect, is what I'm trying to say, because we're splitting. Should have put a null here. That way we can actually look at what it's splitting. So that's it's splitting between this one and this one, because this split over here is saying at paper number equals 0. Now what happens if I go like at paper number equals 1? It's choosing a different coupon. 2. Now where's this paper number coming from? Now the paper number is, if you recall, It was the thing up here, this fancy thing over here with the for loop. And all I'm really doing in this for loop, this goes back to part 1 of procedural modeling series. How I use the for loop, how to use the for loop, and how to use this metadata in order to get the iteration. So let's take a look what this for loop is doing. Now, just gonna take a single pass, and I'm just gonna go like 1. So it's iterating through each square, each coupon square. Template that. Okay. This for loop is iterating through each coupon. And every single time it's going through each square, or which is each coupon, I give it a name. I create a paper number attribute. Where do I get the paper number? From this metadata over here, which is the grabbing the iteration number. Now let me pull this up. If we look into the spreadsheet for this, and down here, so let's take a look down here. And we're gonna go to the details. And you can see there's iteration number right there. Okay, let me go like this. Iteration number. That's where we get the iteration number. Now look what happens if I go to the... Oh, okay. I want to iterate to the next one. Okay, the iteration number is 1 now. So I'm... Okay, this single pass here, parameter allows me to sort of cheat and debug the for loop by skipping to the iteration number, so we can check if everything is working correctly. Realistically, this would not be on. If you want it to work properly, don't turn that on. But it's a nice debugging feature to look inside the for loop. And I'm taking the iteration number and I'm labeling it in my wrangle here, so you can see that I have the paper number here. And where am I getting this paper number? From the detailed of the first input. What do I have plugged into the first input? Which is this guy over there, which is this over here, which is that line that's connected to this node over here. That's one. And then I'm grabbing the iteration attribute, which is this guy over down here in the spreadsheet. 0 is just nothing. It's always 0 at the end. Here it's saying that if you want to ignore the last, if you, primitive point element, changing the name without having to change the arguments as well. Basically, the last parameter, I've always used 0. It's always ignored. I've never had a case where I needed the last parameter of this function to be anything other than 0. You can, in fact, I think you can just skip it, and it may still work. Let me see. Let's take a look. So I have this little test here that I'm doing. Oh, let me get rid of all the overlays. This little test here. I put this group name test here. Let's see. Paper number 0, 1, 2. Yeah, you don't even need the last parameter in that wrangle. So you can just go detailed 1 for the input number and the iteration. So I'm grabbing that iteration number and I'm using that to label my paper number, which is, I should have called it coupon. Coupon 0, 1, 2, 3. Once you have that, this splitting can be used for that. So we go paper number equals 2. I hope I still have that in my clipboard. Oh, thank God. Okay, there we go. So this fancy H script here is basically grabbing that number from my parameter thing, which is that fancy parameter node that I have, because I want to specify, I want like a control board, one place to control everything. So I'm grabbing this parameter value here, that's this guy. Let me use this. Grabbing this parameter number, which is 0 at this moment, and it's saying put it in here. Put it straight, plug it right in there. That's what the number I want you to split, the paper number that I want this splitting node to split to be. So this just is a fancy way to control everything. So let me show you. Let's put the null here, template the split, and I'm going to change the number to tear off on using this node over here. Sorry, everything just keeps flying away. Okay, let's change this. 1, 2, 3. So this is a way to link it automatically. This makes it super procedural. It's nice to have everything controlled. Ah, it went away again. Windows. It's nice to have a place to control everything, one place to control everything, rather than like going up and down. Okay, where's that node? It's over here. Okay, this node is over here, and go back and forth. When you have a really large project, that will be super tedious. Okay, let's change back to that one. Jones. Sorry, it's a little hard to pronounce. Oh wait, I just noticed what that was spelling. Oh my god, Jones. Okay, I'm glad you like your video. I'm glad you like my videos. I just noticed what that said. Okay, where was I? So that's the pinning. So that's where this, the strong points, right. I haven't even gone over the strong points. Where is the strong points? Realistically, okay, there's that split. It happens here, right? So I need to split off the coupon that we are concerned, that we're selecting, that we want to tear off, which is this guy. That's what split it out compared to one that the whole larger paper and the coupon that we're tearing off. That's this gun. Overlays. I forgot to delete the overlays. Okay, we're going to take that and we're going to concentrate just on this coupon. And what do we do with that? That's where all the strong points of the selected match to animation really comes in, because I don't want to pull the whole thing. If I take this whole, select this whole coupon and go like pin all these points and match the animation, well, that's not going to be, that's going to look ugly. Well, okay, it's not going to look realistic, because what that does tells the Vellum solver, it tells the Vellum solver, do not ignore all these points. I want the Vellum solver to ignore the points. Don't do your fancy Vellum calculations, and just move the way I tell you to. So that's not going to end up great. I mean, we can try it. Let's give it a try, actually. It's probably a lot easier to explain. Larger paper. So we have selected strong points, larger paper, static points, strong points, selected coupon. Okay. Let's take a look. So now we're selecting everything. You can see here all these points are purple and all these ones are purple. Well, there's nothing that's changing. The ones at the top has always been like that. What I've done is that I'm selecting the entire coupon to pin down and to match animation. So it tells the Vellum solver, skip your fancy math calculations and just match the animation as I tell you to. And let's take a look let's see what that looks like when we apply it to the Vellum solver. Let's just play it. It's not as great, right? I don't know if you can tell. Look, let's even apply the UV. Oh, let's not actually. I took it out at the top. That's why. I took out the UVs at the top. Okay, let's just forget that. This paper it tears off. Like the tearing looks pretty cool. It's selling the tearing part just because the other side is more natural looking. But this coupon that's being torn out, well, there's no folding, there's no thing, there's nothing happening to it. It looks exactly like our animation. This, and let's take a look at the Vellum solver. It's not moving at all. That's because we told it to. We told this Vellum cloth over here, skip, don't do your fancy Vellum calculations on this coupon because we told it to. That's what we told it to do. And that results in a very unnatural look. Now let's remove this whole coupon. And we're left off with only these points, a few selected points to match. And let's run it again. I know you've already seen what it looks like, but I want you to see a one-by-one comparison. So that's a more natural look because there's more folding. The Vellum solver takes over for part of it. So this is one thing I want you to take away, is that you want the Vellum solver to take over some part of the geometry and control some part of the geometry. So you need to go 50-50. You need the Vellum solver needs to be a part of something, and you need to control how part of the geometry as well. So just select. Don't pin everything is what I'm trying to say. Don't pin the entire geometry. Don't pin the entire coupon. Just pin a part of it because you want to direct the animation. You want to direct, sort of help the Vellum solver. I want you to do this, but without telling you. Can you imagine a manager micromanaging everything you do? That's not what a manager does. A manager tells you, okay, I want you to do a certain task. Now, if the manager goes like, I want you to do a certain task, and I want you to do it this way, and don't do it that way. I want you to do exactly this. Take 1 step forward, take 3 steps left, and take 4 steps, I don't know, in a circle. Who knows? That's, why would you care? You direct it. You don't micromanage it. So that's what I want you to understand, that you need the Vellum solver to take over some part of the geometry. And how I got those few points, because I did that procedurally as well. So we have this whole, let's go back to the split. The split is how I chose the coupon. And we're splitting it out into a different branch. So this, I'm calling it selected coupon. That's the whole entire coupon. I'm using the group expand, and I'm actually going in the negative direction here. So the group expand is going negative, so it's actually shrinking. So if I increase this will increase the group area. If I go down, keep going down, it goes to nothing basically. -3 gives me 1 point. So okay, I'll take that. And I did something super fancy, which was really unnecessary now that I look at it. I used a distance along geometry to figure out the exact middle points. And this was super unnecessary, but I'll explain it as quickly as I can. What it does, it calculates a distance between a selected point. So here it has start points. So the start points is the points that I had in this group expand here, which is this 1 point in the middle. I want the distance of every other point and how far it is towards this point. So to visually see what that means, I added a color node and I mapped the distance to the color. So you can see here that there is red around the border and their green is in the middle, because the green spots are the closest to this expanded point, this point in the middle. They're the closest. So they have a 0 distance practically. And the red is the furthest distance away from that point. And that's why this is red. So this is the values I'm getting. smaller, and as it goes away and away and further, it gets larger and larger and larger until you hit like the edges and there's nowhere to go. And I take that and I go like at distance, because that value is stored in the distance, and I go like at distance greater than, or sorry, less than 0.1. So I want the closest points to that is in this group expand, this closest to this, and I want the closest points to that, which ends up being less than 0.1 distance. It ends up being these 5 points. Now this was very convoluted. I don't know what I was thinking, why I did it this way. You really don't have to do it this way. All you had to do, or I had to do, was let's ignore this. Let's go back to this group expand and just increase this a little bit. I mean, yeah, it's not as great because there's more control points. Go down a bit. Yeah. I guess that might have been one of the reasons why, because it's so low poly that the group expand, there's no way to get in between. Like this is too many points. This is too little. There's just 1 point. And that's probably why I did it this way, with this convoluted distance along geometry. But you can do it a different way too. You can also create like manually select it, or you can choose this choose the center, map a sphere to this center point. So let's blast this point. Let's blast it. And I just want that center point. Selected strong points, I called it, right? Blast non-simple, there. And then just copy 2 points, which is something that we learned from the part 1 series of procedural, in this procedural modeling series, is how to use the copy 2 points to really help us in creating different geometries, distributing different geometries. Oops, I have it the wrong way. There we go. Okay, so we have it there. And then we can put a group. Sorry, this is super messy. Group here. But what I want to do, point, enable select region. There we go. And then now we can control it using the size of this box, this sphere. So this is probably a better, more simpler way, less convoluted, to select these 5 points. So okay, I'll just leave this here. You don't have to copy it down or anything. So this hit file, I will clean it up and it will be available for all the bubblepins memberships. Okay, so I will leave that there, and I'll have fancy comments and notes and tips all over the file. So that's how I selected this. These strong points are it's representing that thumb, or that hand that you have on the coupon, that you hold on to it and you pull it away from that perforated paper. That's what I'm trying to picture in my head. So that you can picture this as a thumb in the middle, which is used for this pinning. Oops, the Vellum solver. It's the pinning and it's pulling it away. So you can tell that I hope you can see that the middle points here are not moving. Those 5 points are really moving. Everything else is. Another thing is, let's finish off this example. Let's see, okay, Vellum weld. Another thing to take away. Where is the paper perforated? Where is it going to tear off? We can sew it together. So if you want, you have to think backwards. When you want to tear something apart, you have to think of how to weld it together. You have to reverse the thinking, because it doesn't, the simulator or the solver doesn't really calculate, does make that decision for you where to tear it off. It doesn't make that decision for you. You actually have to decide ahead of time. You can tell that how I split off this grid into 4 squares. So I knew that I was going to tear it off in one of the 4 squares. So you had to know that ahead of time. Then you can tell that's what the vellum weld does. It will weld it together so it can be torn off a little later. So you have to reverse your thinking. And what the vellum weld does, actually we can do this live. This one's relatively easy. Vellum weld. So vellum weld points. Drop this down. I'm gonna disconnect all that. Let's connect this. Vellum weld. What to weld? Well, okay, let's take a look at the parameters over here. The points. Oh, sorry, I left that overlay box on there. I guess my auto delete mechanism isn't kicking in. That's sad. Back to the drawing board. Okay, so we have here the group type points. Now it's points because I create a bunch of point groups. That's why it's points. So we're gonna weld points to points. So we're gonna, oops. So we're gonna weld this to this. So these 2 groups of points will be welded together. So we can be torn off a little later. Let me actually cheat. What did I do? Overlap, outline. Okay. Let me do this. So let's take a look at what those points are. Okay, overlap. Points. Outline, overlap. So these are the points that I want to weld with. Let me create another. Okay, it looks like the same, doesn't it? It's actually not. Because it's on top, it's lying on top of each other. I need to split it in order to show you what I mean. Selected coupon. Okay. Believe this is the one. Nope. This side. Okay. Okay, let's come over here to the side. A little rough copy. So I'm splitting between this smaller one and the larger one. The larger paper and the torn off coupon. Here, in the torn off coupon, I have a group outline. So I'm taking all the points that are outlining this coupon. And then on the other side, for the larger paper, I only want the points that are overlapping with the coupon area. So the points, the perforated points, or the perforated areas that I want to tear off. So those 2 groups of points will be welded together. The outline, and I called it the outline overlap points. Come back to the weld. Now let's choose that. Outline. Larger paper outline, I believe it was called. This. You can see that we have weld points all over now. And then let's connect this. Just see what happens. Okay, it's not tearing off, right? But it is welded. So it is doing something. Oops, I forgot to delete the overlays again. Sorry. So it is welded. You can see that it's welded. It's just not tearing apart. So we're half the battle. we're halfway there. Stiff coupon. It's not tearing off. So what we have to adjust in the weld is, if we scroll down here, you can see that there's a breaking section for these welds over here. So let's turn this on. And it says threshold. When to break off. Basically, this is saying. Okay, let's turn it on and then let's try it. Let's just try the Vellum solver. Okay, that tears off way too quickly. So let's take a look. One frame by frame. Immediately tears off. That's way too fast. So let's come back here and let's make this threshold a little higher because I want it to last a little longer. I want it to struggle a little bit before it actually breaks off. Let's do 1 because of time constraints. I'm just going to do 1. I believe it was 2. Oh, it was 2. Okay. Let's make this 2 then. Okay, let's run the Vellum solver again. Okay, so that's a bit better. It actually struggles with the tearing before it comes off. So you can see here. It struggles a bit. It's struggling, but it's coming through. So it's coming through and it comes out eventually. Now I want to control this tearing part. I want to control this a little bit more. We can actually feed in an attribute to scale the tearing and to have a different threshold assigned to each point. So each weld point can actually have a different threshold. We can choose this and go scale by attribute. And we can actually give it anything we want here. And it says break threshold scale. Now, I had already created this. Threshold scale. Where is it? Here it is. So in this split, so remember this split here? We're splitting between this guy and the rest of the coupon world. It goes all the way down here. Get rid of this overlay. So this whole part here is the coupon side. And then the other side is the rest of the larger paper. So we're going to focus on the coupon here. There's a attribute randomize. What am I randomizing? Well, I'm randomizing a new attribute, break threshold scale. You can call it anything you want, actually. It doesn't have to be this. And I'm adding this value, but it doesn't matter because this attribute didn't exist before. So add just means, you can have set. It doesn't really make much difference in this case because I didn't create I don't have an existing value, an existing break threshold scale ahead of this. So this is actually initializing it as well. And I'm choosing a random value for this. And I'm willing, choose it by the normal Gaussian. I want this to be between 0 and 1. The range of 0 and 1. But I'm actually scaling it up by 2. So it's actually 0 to 2. So you could just go 0 to 1 for this. And I want to see what it looks like. So I remapped the break threshold scale to a color so I can visually see what it looks like for each point. And this is what I see. Red is where it's closest to 1, which is the highest value it should have for the break threshold. 2 is the highest value. So I should put 2. Okay. So there's the greatest thresholds mapped right here, here, and here. So it's going to be, it's going to struggle a little more over here as opposed to this corner over here. This should break off pretty easily over here because this is white and white is mapped to 0 when this break threshold scale has a value of 0. I'm mapping the value to the color so we can visually see what it looks like. Let's go back down and let's see and see if it's lying. Let's take it. slowly. Okay, so you can see that that part breaks off right away. So that color was not lying. And then there we go. Oh, that's persistent, that corner. I don't think it's coming off. Okay. So this here. So I have scale by attribute. Threshold 2, stress, stretch, stress. You can have different types of breaking thresholds. This one is the easiest one to understand for me. So it's just stretching it and then it breaks off. Like I like that struggle. In order to get that last corner to break off, that persistent point, let's lower the threshold a little bit. I think it's too much. Okay, let's go 1.6 and run it again. Okay, there you go. So I went to the weld and I lowered the threshold just a bit. And remember, you need to scale it by attribute. So that's the break threshold scale that we had, that I had randomized, that random value that we had. It's powering it by that. Nope. In order to get that look. And let's put it all together. Oh, I also have a subdivide. So this is something that we learned in concept. Let me take a look. Believe it was concept subdivide. Here, in the concept, basic concept number 3. Where we have this subdivide here. So I'm dropping this down, but in order to get a more high quality paper look without losing these sharp folds, I added a subdivide instead of using the Vellum post process, because the Vellum post process smooths it all out. And using a subdivide with the open subdivision bilinear, it keeps these folds while adding more topology to the paper if I need it. So that's why we apply what we learned from basic concept 3, and I added a subdivide to our coupon. That's what that is doing. Let's see. And it's good to note that I actually used a really low stiffness value just because I want. So this sort of breaks that paper effect rule that I sort of kept nailing in your head at the beginning. The low stiffness value to sell the paper effect. Well, here I kind of did the opposite. I did, high stiffness value to sell the paper effect. This, I kind of did the opposite. I kind of lowered it so much. Like I made it so low. And why would I do that? It's because I like this stretching. Where that struggle. Okay, I need a higher threshold. Breaking threshold. I really like this struggle. That struggle. It's like it's tearing. It's like this tearing apart from perforated paper. It doesn't break off until there's a bit of struggle. That's what I was going for. So that's where I broke the sort of unwritten rule of lowering the stiffness value. I still got a paper effect though, but for in this case, once it goes this, it's a little. This is a little not as rigid as I would like. Because once you tear off a coupon, it sort of stays in place. It doesn't look like this. This looks like cloth right now. So improvements could be made. Probably a little, if I go a little fancier and have the stiffness change or the pinning. Pin the entire coupon, which I told you not to do, but pin the entire coupon down. Like this, pin it all down, except break the coupon, break the pinning points once the top, the welds break. So actually have the pinning points change over time. And that's something fancy that would actually add to this effect to make this, to sell this coupon perforated tearing apart look. All right. I don't think I even made it for the last example. Didn't even make it to the last example. Didn't think that would happen. I thought I would make it. Okay, I guess that would have to be saved for the next time. So we managed to get through the scrap paper, the coupon tearing, but I couldn't make it to the posters or paper flying through the city look. So that will have to be the next one again. Cool. Okay. We'll have to leave it at that just because I'm super tired right now. I will clean this file up. So this file will be available for download for all the bubblepins memberships. Give me a couple of days to clean it up, put my notes in, put some comments, and yeah, really clean it up. And I'll probably get rid of this parameters to this one here, just because or maybe map it to a relative folder. So because not everyone has this environment variable set up. This is sort of like very personal location on my hard drive. It won't work for you. So I might just get rid of this or map it to a more useful area for you. So Birdie Academy, I was waiting your live today, but my laptop crashed and I will watch it when... Oh yeah, no problem. Replay is always available. No problem. Alright, so that wraps it up for today. I hope you enjoyed today's lesson. I do apologize not being able to manage to get to the last example, the paper flying through the city. That was a good example too. It's really good for large scale scenes. Especially, I'm working NG on Vellum courses and your tutorials inspire me. Awesome. I'm glad you like it. All right. If anyone has any questions, just leave them in the comments and I'll get back to you as soon as possible. Let's see. Yeah, that's about wraps it up. So thank you all for joining me today and for another really long stream again. I have to try and manage the time a little better next time. All right. I'll see everyone next time and happy Houdini.